What the heck?
Hectogon.
Hello, subjects. Today I have something quite cool for you. Something that I've been wanting to materialize into a mathematical answer for quite a long time, because I've had a solution, a numerical answer, but I never had a closed form answer. Not that this answer necessarily counts as closed form, but it's very interesting nonetheless. But what's the question, right? How do I know what the answer is to a question I don't know? So the question is a little vague, but it's got a very cool answer. The question is, when is an eclipse, a solar eclipse specifically, when is an eclipse half over? Now, you can sort of mull this over in your mind, and you can come to a pretty obvious and not too interesting answer. From our perspective, we're assuming a few things. The sun and the moon appear identical in the sky, so these are perfect circles in the sky, and they're completely the same size. The moon moves at a constant linear speed. That's how it more or less appears to us. A constant linear velocity more or less appears to us in the sky. And so, because it's moving constantly, of course, the eclipse is half over when the moon covers the sun, because then it has to uncover it. So actually, I'm going to rephrase the question. Because the moon moving off of the sun is a mirror image of the moon moving onto the sun, we're going to say the eclipse starts when they're tangential, and it ends when the moon perfectly covers the sun. Okay? So you would then obviously say that the eclipse is half over when the moon, the front point of the moon is exactly at the center of the sun. That means it's moved one radius length across the sun, and it has one radius length to go. So in time, that's when it's half over, when the point of the moon that was once tangential to the sun is now halfway across it. But that's just halfway in time. That's not very interesting. A much more interesting question is, when is it physically half over? When is half the sun covered? How far, what fraction of the diameter of the sun does the moon have to traverse to cover half the area of the disk of the sun? And now this is much less obvious, and it's very, very cool. Let's talk about it. What we're going to do is address this problem in its own standalone video, because it's a very, very interesting question. So I'm going to get one more color. We're going to do orange for the sun, and we're going to do light blue or bluish for the moon. And we're going to explore this question. When is the sun half covered by the moon? Very, very interesting question. So the start of the eclipse is going to be defined like this. It's going to be when the moon is completely tangential to the sun in the sky. So these are supposed to be circles that are exactly the same size. I'm sorry that they aren't, but they are supposed to be, for the sake of simplicity, circles of radius 1. So whatever the apparent size of them in the sky is, the radius of that is 1. And we'll say that the center of the sun is the origin of the graph. So the sun is not moving, and the moon is moving onto it. Right? And we want to know when the sun is half covered. So the eclipse will be over. We'll say these are the definitions of beginning and end of the eclipse. The eclipse will be over when the moon completely covers the sun. And that instant in time is when the eclipse is finished, and we want to know, when is the sun half covered? Obviously, the eclipse is half over in time when the moon, when this point, the furthest left point on the moon, goes from here to the middle of the sun. Obviously, this is not when the sun is half covered, because we could easily just draw this diameter of the sun right here and see that there's still half of the sun to go right there. And half of the sun plus these little wedges things here has to amount to more than half, which means this little crescent, not crescent, but eye shape in the middle cannot be half of the area of the sun. It must be less than half the area. And so we want to know, when is that fancy schmancy shape actually half the area of the sun, which would mean this shape here, the lune, I think it's called, would also have to be half the area of the sun. So we want to find that balance. How far along the diameter of the sun does the moon have to go before it's covering half of it? So that's the question we want to answer. So to answer that question, we sort of need to take a look at this shape right here. But I will do it with a new picture. So we want to consider the unit circle in the plane, centered at the origin. And we're saying we want another circle to come in and overlap it like that. That's the exact same size. So the center is moving towards the center of this circle. And we want to find the area of this right here. Right? And if we do that correctly, then we can simply multiply it by 4, 1, 2, 3, 4, to get the area of the eye shape in the middle, right? So how do we calculate that area? Well, I told you that this is the unit circle, which means it's represented by this equation here. It's represented by x squared plus y squared equals 1. And so if we solve for y, which will give us this upper half of the circle here, we get that y is equal to the square root of 1 minus x squared. So that gives us that function up here. Now, to find this area, we simply need to take the area under the curve, or the integral, the definite integral, from whatever this point is to this point here. Well, since we said that this is the origin, and this is a unit circle, this point must be 1, 0, which means we'll be integrating up to 1, but we don't know what this point is yet. Let's call it x. So we'll call that point x, which means we're going to take the integral from x to 1 of this function here, the square root of 1 minus t squared dt, but we want 4 of them, right? So we have to multiply by 4. So this will be the area under this thing right here, and we just want to multiply it by 4 to get the area of the entire eye shape. Well, what is this? What is the antiderivative of the square root of 1 minus t squared? As it turns out, it's equal to t times the square root of 1 minus t squared plus the inverse sine of t all over 2. But what we're doing is we're multiplying it by 4, and we're evaluating it from x to 1, right? So that's this is just the antiderivative of this function here. So if you want to work that out, that's fine. I'm just telling you what it is right now. So we're plugging in 4 divided by 2 is just 2, and so we're plugging in 1 to these things. If we plug in 1 into here, we get 1 times 1 minus 1, and 1 minus 1 is 0, the square root of 0 is 0. If we plug in 1 into the sine of t, the inverse sine of t, we get pi over 2, because the sine of pi over 2 is 1, the inverse sine of 1 must be pi over 2. So we're going to get 2 times 1 times 0 plus pi over 2. And now we're subtracting the case where we plug in x, right? So we get minus x times the square root of 1 minus x squared minus the inverse sine of x. Simplifying this expression, this goes away, the 2's cancel, we bring in the 2 there, and we get pi minus 2x times the square root of 1 minus x squared minus 2 times the inverse sine of x. And so we now need to set this equal to half the area of the circle so that we can figure out which point along the radius, or along the diameter, will give us half the area. So we need to set this equal to pi over 2, which means we need to solve, rearranging all the terms and canceling things out, we need to solve this equation here, right? Because half the area of the circle is pi over 2. So in this case, we would need to solve for x. So good luck with that, because we have the horrendous fact that, we have a radical times a polynomial minus an inverse trig function, and you're supposed to solve for x. Like, that's ridiculous. I mean, it's impossible to do that. So obviously, the best way to approach this problem cannot be in the linear sense, just treating the point, the point along the diameter from left to right. That simply isn't the way to solve this problem. As you can see, the number that would solve this would just be horrendous. So it obviously can't be the right way to look at this. So this can't be it. What we want to do is we want to keep this. We want to keep this fact here. We know that this has to be the area under the curve, right? This is the area we're looking for, and we do want to solve it, right? We just don't know how to do that yet. We do want to solve that equation, whatever the answer may be. But it simply isn't the way to do it with this weird, mix of inverse signs and things like that. So there's 2 times the inverse sine of x right there. It's a little off the screen, but you don't really need to see it. What we need to do is realize another way to completely visualize this problem. So here's the moon, here's the sun. What we actually want to do, instead of talking about it in the left-right sense, is we want to actually talk about this central angle right here that subtends the arc between the intersection points of the circumferences of the moon and the sun. So we will call this theta. So this angle is theta, which makes this angle right here theta over 2, right? So this whole thing is theta, which means this little half angle here is theta over 2. Now, given that this is the unit circle, which makes this 1, that makes this x-coordinate here the cosine of theta over 2. So if we were to put this x in terms of this angle here, this would just have to be the cosine of theta over 2, right? Does that make sense? All I did was rephrase this point along the x-axis in terms of the angle that's created by these two intersection points. And you can imagine these opening up like this as the moon covers the sun. And when the moon fully covers the sun, they'll both be right here because it's opening up halfway. It's opening up all the way, and the moon completely covers the sun because the two intersection points are now the two top points of the moon touching the top and bottom points of the sun. And when they're just tangential, theta is 0 because they're closed to this point right here where the moon is touching the sun. So as the moon covers the sun, these 2 points move up along here, and the angle between them widens and goes from 0 to pi, right? I hope that's clear as to what I'm talking about. So the eclipse in the angle sense starts when theta is 0 and ends when theta is pi, because it opens like that, right? And I will link to the Desmos graph that I made to illustrate this in the description, so that you can see this visually happening for yourself. It's quite a lovely graph that I made, if I do say so myself. It's even color-coded, which is beautiful. So it turns out that the trick that we want to do is just replace the input x with cosine of theta over 2. And then we want to solve for the angle, right? So we know, I'm going to rewrite this so you can actually see it, that if this were x, right, we just solved that this had to be equal to pi minus 2 times x times the square root of 1 minus x squared minus 2 times the inverse sine of x, right? We just solved that. But now we want to sort of shift our perspective to the angle theta. So now we want to find this. We want to find 4 times the integral of cosine of theta over 2 times to 1 of the square root of 1 minus t squared dt. But all that requires is that we simply replace every x in here by cosine of theta over 2, which isn't too difficult. So we end up with pi times pi minus 2 times cosine of theta over 2 times the square root of 1 minus cosine of theta over 2 squared minus 2 times the inverse sine of cosine of theta over 2. And you may be saying, what the heck, Sam? You're really overcomplicating this expression. But what we just did is absolute magic, because it's about to get a whole lot simpler. Because what's 1 minus cosine squared? Well, 1 minus cosine squared is just sine squared of whatever the angle is, which means I can just replace this with the sine squared of theta over 2. But of course, I'm also square rooting that, so the square and the square root cancel. And now I'm left with 2 times cosine of theta over 2 times sine of theta over 2, which is actually the double angle formula for the sine function, right? 2 times cosine of x times sine of x is all equal to sine of 2x. So this, right here, has to be equal to the sine of 2 times theta over 2, which of course just cancel, and we're left with sine of theta, which is absolutely magnificent. So a brilliant simplification. And now if we take a look at this, we have to do some triangle stuff. So let's take a look at what the inverse sine of cosine of theta over 2 might be. So we're taking a look at this angle, and we know that the cosine of theta over 2 is whatever it is. It's x. It doesn't really matter. What would therefore be the inverse sine of cosine of theta over 2? Well, sine requires opposite over hypotenuse, whereas cosine requires adjacent over hypotenuse. So the hypotenuse isn't going to change, but we need this side to now become the opposite relative to some angle. And it's opposite relative to this angle here. Since this is a right angle, this angle must be pi over 2 minus theta over 2, because this is pi over 2, because it's a right angle. This is theta over 2. This must be the complementary angle. And so the sine of this angle gives me the cosine of theta over 2, which means the inverse sine of theta over 2 has to be this angle, which means this is this right here. Okay? I hope that's clear. We just did some trig stuff. So that means that our whole equation, put in terms of the world of theta, simplifies drastically. Because what we end up with, instead of pi minus 2 times cosine of theta over 2 times the square root of 1 minus cosine squared of theta over 2, all minus 2 times the inverse sine of cosine of theta over 2, we end up with a drastically simpler equation that simply reads pi minus sine of theta minus 2 times pi over 2 minus theta over 2. Distributing the 2's, we get pi minus sine of theta minus pi plus theta, which simplifies because the pi's cancel, and we get theta minus sine of theta. Now this is the area of this whole thing right here, this whole eye shape right here, in terms of this angle theta here, this full angle theta, right? Which is drastically simpler than this expression here. But remember, all we have to do now is set this equal to pi over 2, because that will be half the area of the circle of radius 1, which has area pi. And this is about to blow your mind, because this is going to tell us what this lovely angle is here. This beautiful angle that will give us half of the sun being covered by the moon. So we need to prove, or we need to find theta such that pi over 2 is equal to theta minus sine of theta. Now, I need to take a little detour. This is the equation we need to solve. We need to find theta that makes this equation correct, and that theta will tell us exactly what angle the moon has to, or whatever angle has to subtend the arc of the intersection points of the moon and the sun, so that the moon is covering half of the sun. First, we need to talk about a little something on the side. We need to talk about something called the Dotty number, which is the unique real solution to the equation cosine of x equals x. So the input being the same as the output of the cosine function. So this point is about 0.739 and can be calculated using the Lagrange inversion theorem with the function x minus cosine of x. And it's actually an attractive fixed point, so if you plug in any number into cosine and repeat the cosine again and again and again, it will always approach this number called the Dotty number, D-O-T-T-I-E, which is the nickname of my grandmother Dorothy, but no relation to her in this regard. So it is the unique solution, so we'll call it D, right? We'll call this D, capital D for the Dotty number. And so it's the unique solution such that D is equal to cosine of D, where D is a real number. And the reason we need that is because it's about to crop the heck up. So this is a unique solution. It's the only real number that does it, and it's the only attractive fixed point of the cosine function. Read up on attractive fixed points. They're very interesting. So the reason we need that is because we can turn this into a cosine question. All we need is the fact that the cosine of pi over 2 minus theta is equal to the sine of theta. Because cosine and sine are complementary functions, which means if you plug in complementary angles, you get the same number. That's a pretty well-established fact. I've shown that on my channel loads of times. But not only that, cosine is an even function, which means it doesn't care about sine, or multiples of -1. So I can flip this difference, which would be akin to multiplying the inside by -1, and it doesn't actually change the value, which means this is exactly equal to the cosine of theta minus pi over 2. So I can simply replace this sine of theta with this right here, and I end up with pi over 2 equals theta minus the cosine of theta minus pi over 2. Now I'm going to move this over, subtract the pi over 2 over, and we are left with the result that theta minus pi over 2 equals cosine of theta minus pi over 2. But look at that. We have the input being equal to the cosine of that input. And since this angle has to be some real number, there's only one number that satisfies this equation, and that's the Dotty number, because we're saying the input is the same as the output, right? Which means, dun-da-da-da, that theta minus pi over 2 has to be equal to this mysterious dotty number, which means the angle that we're looking for, ladies and gentlemen, that will cause these 2 points to be such that the moon is covering half of the sun and this crescent shape will be equal to the eye shape, is precisely the dotty number plus pi over 2. This is 0.739, and this is about 1.57, so you get a number with a numerical value of about 2.30988 radians. This is almost certainly an irrational number. I would be gobsmacked if it wasn't. And this is the numerical value that I had as an answer to this question for so long, but didn't think to simply transform this equation into this so it would reveal that the dotty number is related to this, which is just wicked cool. So the angle that this has to open up to, subtending these 2 intersection points, is precisely the dotty number plus an extra right angle turn, or pi over 2 radians. But remember, I didn't ask what angle it was. I wanted to know what fraction of the diameter of the sun the moon has to cover for it to cover half of it. But that would mean I'd have to figure out how far this distance is here, right? The distance this distance right here. The distance that the moon has covered from moving from here to here, right? So at the point where the angle opened is the dotty number plus pi over 2. How far along the diameter of the sun has this leftmost point of the moon traveled? And it's not that hard to figure it out. We just need to figure out what this distance is in terms of theta and plug this theta into it, this 2.30988. And it's not that hard to figure out, right? Because if this x-coordinate is the cosine of theta over 2, then this distance here must be 1 minus the cosine of theta over 2, which means that this is twice that. So the distance that the moon has traveled across the sun, given theta, is precisely 2 times 1 minus the cosine of theta over 2. That is the distance along the sun that the moon has traveled. But this will tell you how many radius lengths it's traveled. So once it's covered the sun, you're going to get 2. But I want to know what fraction of the diameter is covered. So instead of putting it in terms of radius lengths, we want to put it in terms of the diameter. So I'm going to divide by 2. And so this will be related to the diameter instead of the radius. So given theta, it'll tell you the fraction of the diameter that the moon is covered. So at theta equals 0, this is 1, and we get 1 minus 1, which is 0. At theta equals pi, we get cosine of pi over 2, which is 0, and we get 1 as a result. So at pi, it's covered the entirety of the sun, 1. It's covered, the entire length of the diameter, 1 diameter. At 0, it's covered 0% of the diameter. So we want to know what fraction of the diameter it is when the angle is this angle, right? Because this will be when the moon covers half the sun. And if you plug 2.30988, or the dotty number plus pi over 2, into this equation, you end up with a number that is about 0.596, which means when 59.6-ish% of the diameter has been covered by the moon, that is when the sun will be half covered by the moon. So not a very nice, easy answer to understand in the sense of regular numbers, but let's take a look at what that might look like. So it's just about 60% of the sun's diameter being traversed by the moon will cause half of the sun to be covered. So if we sort of imagine that's the center, there's 1 radius length, which means this is 50% of the way, right? So 60% should be right about there, which means when the moon does this, if these were exactly the same circles and exactly the same size, sorry that they're drawn so poorly, just imagine that they are for a second, then this, so when this length, if the full diameter of the sun were 1, then this length is going to be 0.596 about, then this lune is precisely pi over 2 in area, which means this eyeball shape is also precisely pi over 2 in area. And so the two facts are that this is about 60% of the radius, of the diameter, and this angle here, which subtends the arc between the 2 intersection points, is precisely this amount of radians, the dotty number plus pi over 2. Go read up on the dotty number. It's very, very interesting. Has a very cool series representation in terms of odd powers of pi. Very cool. There's no known closed form for it, but it's a very interesting number. It's very cool to read about attractive fixed points, but I just figured this was an interesting enough question, and the answer in time is boring, because that's just when it gets halfway across the sun. I wanted to know when the sun was half covered, and it turns out that combining these two very simple shapes and asking such a simple question yields a very, very unexpected and interesting and difficult answer. The Dottie number plus pi over 2. Very unexpected. So I hope this was a cool foray into a physical question involving very basic, I would say calculus 2 maybe, since getting into integrals of these types of functions is really calculus 2. So I hope this was cool. Thank you for watching, and I'll see you next time.